Professor Ravi and Kannan.
Yeah, thanks for the intro and thanks for the invitation and thanks for listening. So, as the title says, it's determining K, whatever K is. I hope I'll make it clear. It's joint work with a number of people at IISc as well as Microsoft. Now, I'm going to introduce this by saying this is something to do with learning from positive examples. If it was not a theory audience, if it was a machine learning audience, I would say this is unsupervised learning, basically the same thing. Because if you're given only positive examples, there's no point giving labels, right? So standard pack learning, you're given examples which are in a polytope. You want to learn a polytope. You're given examples which are in the polytope and examples of points outside the polytope, and you have to learn K. And the difference now, I'll come to the difference. The examples may be generated by any distribution in general. The thing we are going to talk about, the departure is in many areas of this topic modeling, community detection, and various clustering problems will be examples. These are all unsupervised learning problems. The way we'll think about it for this slide is it's as if you're given only positive examples. They're all problems of learning a polytope, by the way. In a way, I'll make that clear. So you have to learn an unknown polytope, but you're given only positive examples. For example, topic modeling will be one of the examples I give you. You're never given non-documents in topic modeling, or in Gaussian mixtures, you'll never be given non-examples, right? So you'll be given only examples. That's all I'm saying here. You can think of it as unsupervised learning. The distribution now cannot be arbitrary because I have a big polytope. I want you to learn. If I concentrate my distribution on a small subset of it, you obviously cannot learn the whole thing. If I had given you negative examples, they would have been outside and you might have learned it, but now not. So I better restrict the distribution. The data is often generated in two steps. I'm not going to give you plain good examples in K. I pick first a random point X and K for picking one data point. This is a generation process. And then I pick data point Y. All I tell you is that the expected value of Y given X is X. X might be the probability vector with which you generate X with which you generate Y, as you'll see. Y is not necessarily So Y is not necessarily in K at all. The problem is I'm giving you IID samples of Y, but not X, not points necessarily in K. Learn K. So let me put up a picture first. The red points are data points that I give you, but they're generated in a two-step process. I generate a black point 1 first, and then generate a red point 1, whose expectation is 1. It can be sort of around there. Expectation is black 1, right? But I don't give you black points. I give you only the red points. As you can see, several of them, in fact, in general, quite a few of them can be outside the polytope that I'm trying to learn, right? So I'm going to give you a couple of examples. So this talk has a lot more questions than answers. I'll formulate the questions for these examples. I'll solve the problem for topic modeling, but not the others. Sorry? The distribution is so far arbitrary, but I'm going to put conditions on it, and you need not learn the distribution. You just need to learn the polytope. So in topic modeling, quick intro, topic vector is a word frequency vector. So if there are 10,000 words in the dictionary, I have a 10,000 dimensional vector giving the probability of each word. So they must add up to 1, non-negative, and so on. A document is also a word frequency vector. That's what's the relative frequency of each word in the document, right? There are K unknown topics, and little k is the K that you want to learn. That's the title of the talk. The convex file, topics are vectors, right? So the convex file of the vectors is a polytope K. You can think of it as either wanting to learn topics or the convex file, because it's just all the vertices, right? Documents are independent. They're generated as follows. To generate document J, I come around and pick a random probability vector in the topic polytope. So this Pj is a convex combination of topics, because the vertices of K are topics. And then I pick some number of words of the document in IID trials with Pj as a multinomial probability. So the P1j gives you the probability of word 1 and so on in each of the M trials. And all I give you, this is the red point, all I give you is a document vector, which is the count of each word divided by M because I picked M words. Only A is given. So only the red points are given to you, right? It's data. Now, M is often just very small constant. The number of samples may grow, number of documents, but the number of words per document often doesn't grow. It's an easy calculation to see that the variance is 1 over M summed over all the words. So the variance is constant, or the standard deviation is constant, right? Now, topics are also in general, I'm not giving you examples here, but topics are in general constant apart. So we come to the first difficulty in these problems, and this will be accentuated in the other examples. The distance between the document and its generating probability vector. So the black and red point in the picture, the distance is comparable to the distance between topic vectors. So it's comparable to the scale of the polytope. So the polytope scale is 1. The red and black points can be separated by 1/2 or 1/3 or something like that. So they can be very far apart. And that's the major problem in all this. So because of this, if I take the convex hull of the document, which is all the data I'm given, that's no good as an approximation to K. You saw that in the picture. The red points, the convex hull is much bigger than the black points, right? So that's one difficulty. Now we want even a simpler problem just to learn the number of extreme points of K, not necessarily K itself.
So does this imply that the scale that manages by some constant independent dimension factor, you won't capture all the way?
So if you expand the polytope by a constant, you will potentially capture, but you'll get a lot of junk in the sense a lot of probability vectors will not be there. So in a sense you can say learning within some approximation the polytope may be doable, but it may not give you that's not the problem we want to solve, right? So yeah.
How different is it from adding noise to a sample?
Okay, so you may think of it as noise, but noise may mislead somebody because this is intentional generation of points. But certainly the difference between red and black you can think of as noise. Normally when you think of as noise, you don't think of noise dominating the data, which is the black point. Here it does. Here the scale of the noise, it didn't dominate yet, it's comparable. The next example will dominate. So that's why I didn't call it noise. Yeah, but you can think of it as. Okay. So Gaussian mixture is another example. Your NIID samples from a mixture of K spherical Gaussians. I should have drawn pictures for all this, but I was lazy. With means separated by constant number of standard deviations, let's say. So the way you can think of this as a two-step process again. I come around, I want to pick a point, I pick one of the Gaussian components, namely I pick its center, let's say, and then I pick a data point, AJ, with that as center. Okay. So AJ, the expected value of AJ given PJ is PJ, but the variance is large again. So in d dimensions, the standard deviation is 1 in each direction. Points are in general root d away, right? The variances add up in the d variances. So points are root d away, d large. This is extremely large compared to what I assume as a separation between centers, which is only 10 standard deviations, 6 standard deviations, whatever the famous. So you can now, in this problem, topic modeling is like as if you think of infinite mixtures, where Pj can be a random convex combination of the k-means, and then you put a Gaussian around it, so infinitely many Gaussians. Okay. The polytope of interest that you want to learn, you can think of as the convex hull of the means of the Gaussians. And it turns out if you learn that, you've done the job. We won't see that, but that's really learning a polytope problem. Okay. So I want to give you one more example, overlapping communities where noise in the sense is swamps data. So n people, each is an n vector of probabilities. Well, person is represented by the probability that the person knows each other person, right? So it's an n vector of probabilities. Okay. They don't have to add up to 1. They're each between 0 and 1, but they don't have to add up to we hypothesize that there are little k communities. Each community is also an n vector. And what it signifies is, if you purely belong to one community, these are the probabilities that you meet each person. Okay? You can ignore the interpretation if you like, because verbal interpretation is more, you can just think of it geometrically. So the convex file K is the community polytope. Person J, people are IID, they are generated as follows. You pick a point in the polytope. Another way to think about this is, you pick the person to be fractionally belonging to each of the communities. The fraction should add up to 1. Okay? So people are not purely in one community, but they can be in different communities. And then you pick a 0, 1 vector, and the 0, 1 vector says, actually, did you meet the person or know the person or not? And it's 1 with probability Pij. So you randomly meet or not meet with these probabilities. Only the 0, 1 vector is given, right? The probabilities are not given, of course. Right? So the stochastic block model, which many of you might be familiar with, is a special case when people belong just to one community. It's pure community model. Okay? This is a more general model which has been studied a little bit, not as much as topic modeling, but it's been studied as well. So let's take two communities. Let's take a very simple model where the probability of two people meeting in the same community is p, and 0 if they are in different communities. Okay? The squared distance between community vectors, it's easy to see, is np squared under this definition. But the variance, unfortunately, is np. This is all just Bernoulli, it's an easy calculation. So p is often little over 1. P can be as small as 1 over n. You only know a constant number of people in general. That's the same as saying probability of meeting each person is 1 over n. So in that case, you see the distance between what we consider noise, the distance between the red and black points, is in fact much greater than the distance between the vertices of K. Yet, I give you only the red points, the AJ, you have to learn the polytope. Okay? So, determining K. So, in these examples, I talked about learning the whole polytope. Let's look at a simpler problem, learning the number of vertices. I just want to know the number of communities or the number of topics. That's the first problem I want to solve. The reason that's interesting is in most of the literature, not completely all, but almost all the literature, the starting point is an assumption that K is given to you. Okay? So that's the problem we want to tackle. And I won't fully solve that. I'll tell you a nice conjecture which would be nice to prove, but I'll be able to solve this problem for topic modeling. That's what I want to show you. So I want K to be not given. So there are two questions one can ask. The first simpler question perhaps is there a good data determined rather than generating model dependent? If I give you the generating model, I know K, right? But I don't, the model is hidden, so of course you don't know the model. So from the data, can you get a definition of K that is correct, that is the same as the model's K? So I gave you only the red points in that picture, and you have to tell me they came from a triangle, which is 3, right? That's the problem we want to solve. And perhaps a more interesting problem in practice is there an algorithm, preferably linear time, because knowing K is a starting point for most algorithms on topic modeling or community detection, all these areas. It's only the starting point, or Gaussian mixtures. So you want to solve it fast. Okay? In fact, in linear time would be good. Okay? So we answer these two questions for topic modeling here. A quote-unquote grand general answer is open, and I will formulate a conjecture which would be nice to prove, perhaps generally. Okay? So here is a data-determined definition of the number of topics, just for topic modeling. So we saw that I have a polytope. If I concentrate my probability mass on a subpart of it, then there's no hope of learning the polytope or number of vertices or anything. So let me avoid that by saying that there is substantial mass near the extreme points, near the vertices. So there are what are called pure documents. So for every topic L, and for every document, the probability that Pj is the point inside the polytope, is the convex combination of topics. the probability that Pj puts weight at least 1 minus epsilon on the topic is at least epsilon. What this is saying is almost purely the document is going to be on topic L, but for an epsilon exception, but only with a small probability. I have to guarantee this. There's one way of guaranteeing there's probability mass near the vertices. The vertices are just pure topics, and I have epsilon mass at least, some mass near each of the vertices. That's what this is saying. So another obvious necessary condition is that topics are distinct. So I'm going to assume what are known as catchwords. Catchwords are sort of words distinct to each topic. So for every topic L, there is a word IL, which is a catchword, which has, now MIL is the weight or frequency the topic L puts on word I. You don't have to absorb all the notation because I've written, or at least will say verbally what's going on, and perhaps that's easy to remember. So this is saying the catchword for topic L has higher frequency in topic L than in any other topic by a definite amount. Okay? So there's one word per topic which occurs more frequently, strictly more frequently in that topic than other topics. Okay? These two conditions have a long history. They're not something I made up yesterday. Perhaps the first formal study of this is a paper by Christos, Santosh Paul and others. They were trying to study something called LSI for topic modeling. So also it's in a paper with Chiranjeev and others that I wrote in 2014, these two assumptions. So they've been around. First is necessary, second or some version of the second is also necessary. We make another technical assumption. It turns out you need at least a constant number of words, big constant number of words per document. So if I give you only one word per document, the variance is too high to do anything. Okay. Now, if I magically gave you, so there are epsilon n pure documents for each topic in expectation, but there should be that many roughly. If I give you those pure documents for one topic at a time, their average is a good estimate of the topic, right? So I have all the probability vectors near the vertex for these documents, and I generated the documents by just averaging out. I'll get just Herfting-Chernoff will tell you that's a good estimate of the polytope. So if I got these sets of pure documents, I'm done. Okay. Of course, I don't have them. Don't know the pure documents. Now, instead, so I'm going to do the following. I don't know which epsilon n documents are pure for each topic, but I'm going to try all subsets of epsilon n documents, okay, and take their averages. Intuitively, first, this is clear. It's easy, not even intuitively. All these averages lie in or close to the convex set. Because I'm averaging so many points, the noise cancels, right? They are random points. You can prove that that is true for every set, every subset. Now, what's less clear, but is also intuitively at least hopefully clear, is that exactly k of these averages form extreme points, because only the pure documents around the extreme points average to the right thing. So while this is intuition, proving is not that simple, so I'm going to state a conjecture and a theorem. So there are n IID documents, n is large, going to infinity. I take all the n choose epsilon n averages of epsilon n subsets of documents. I want to assert first that convex hull has a limit as n goes to infinity. It has to be proven. I don't have a proof. This is conjecture, right? And secondly, I want to assert that's equal to the starting polytope you started with. But you need conditions. I didn't put down the conditions here. It'll be nice to prove it under minimal conditions. That in fact, you can recover the limit polytope, the limit data polytope after this averaging gives you the polytope you started with. Okay. That'd be nice to prove. And a simpler thing which would be nice to prove is little k is the number of extreme points of W. Okay. And if something like this is true, possibly also in the other cases that I told you, that would be a nice theorem. What I can prove at this moment, this is theorem 1. It answers the question of a data determined definition of little k. And we'll later tackle the algorithm question. So K is in fact the minimum number of extreme points of a polytope W prime, which is roughly W. So it's contained in W, and W is contained in W prime plus epsilon. I mean to include all points at L infinity distance epsilon from W prime here. Okay. This is epsilon times the L infinity ball of radius 1. Okay. So this I can prove, right? But it'd be nice not to have to do this epsilon fudge. It'll be nice to just prove that. Any questions before I go on? I notice I'm not doing badly on time. Okay, so we can. So I started by saying I want a purely data determined definition of K. This doesn't seem to be, because there are these parameters. It turns out you can make them purely data determined. I won't go into the details of that, because I now want to focus on the algorithm, which will be efficient. This algorithm is not efficient. Obviously, it's exponential time. I've got to take the averages of all these points and convex solve. Okay. By the way, one nice thing is, if you're familiar with the ellipsoid method, even though there's exponential number of points, there's a nice polynomial time membership oracle for the convex set, because there's a nice optimization oracle. So that's an aside. Okay. But it's still not so efficient. It's still not linear time. So, okay, now part 2, a linear time algorithm. I packed into one slide, and I'll go over this slide fairly slowly, the ideas of the linear time algorithm without giving you all the details. So I want to find little k, and we saw that it's a number of vertices, but it's also the number of sets of pure documents, because each vertex had pure documents associated with that vertex, with that topic, right? So question. So if I can identify the set of pure a set of pure documents at a time, I'll be done. Can perhaps we identify pure documents for topic L by saying those are the documents with high frequency of the catchword IL? That's almost tautologically true, right? IL is a catchword for the topic, it had high frequency. That's correct, but it's not so simple, because pure documents are things that have weight almost 1 on the topic, but the weight put on the topic by documents sort of grows continuously down, so there's no sharp drop. So I cannot distinguish pure to not pure so easily, algorithmically. So all of this is going to be intuitive description, so bear with me. I mean, I don't have formal proofs of this. So this cannot be done algorithmically, at least I don't know how to do that. So we are going to have to make an extra assumption, which is called the dominant topic assumption, and that says the following. For each document, so each document puts weight on every topic. It's a convex combination of topics, right? That's how we pick a document. We come along and take a black point inside the simplex by taking a convex combination of the vertices. So it puts maximum weight. The probability of tie is 0, is measured 0, so it puts maximum weight on one topic, some topic, and we assume that the maximum and the second maximum are distinct by a certain amount. This turns out to be generally true. It turns out to be for the distributions that people use to pick weights on topics, which is a Dirichlet distribution often. Okay. So we assume there is this gap. Now with this gap, we can do the following. So we take all documents that put their maximum weight on topic L. So every document puts maximum weight on something. Let's say these are the documents that put maximum weight on topic L. Okay. And then we can show, this is intuitively clear, but it requires a proof. I won't do that. Frequency of catchword for topic L for documents that have max weight on L is strictly greater than the frequency of the same catchword on documents that don't have maximum weight on L. And this uses the fact that the second max is strictly by a certain amount smaller. Okay. So this J prime will put strictly less than 1 by strictly less than max weight by an amount delta. So then you get this. Okay. Again, it's more intuitive than precise at this point. So this what this says is that if somebody told you what the catchwords are now, I can identify pure documents by just saying those are the ones with high frequency and there is a drop. There's a clear drop, okay, which you can see in the data. Now, the trouble is that you don't know what words are catchwords, so non-catchwords might give you a different drop, and there's no way to tell which ones are correct. So, how about a non-catchword I? Say I puts maximum weight on a topic. Each word also has weights on topics, right? Occurs with a certain weight on each topic. So take the topic on which it occurs with most frequency. Then frequency of I on pure documents is high, but that's not good enough. I want it to be high. So this set includes documents which are pure for topic L, that is weight almost 1, but weight could be less than 1. So this better be true for all of these T things, all of those things that put maximum weight on topic, the same topic, right? So we want to ensure that there's no steep fall in frequency or within this. So if you have that, here is the picture then. In summary, all of this together says, I take docs with high frequency of word I, call that SI. If I had a catchword, that's precisely almost documents that put max weight on L. Catchwords are good. They distinguish pure documents, dominant topic from the others. So the high frequency set is TL. What about non-catchwords? Non-catchwords, we ensured there's no steep fall in frequency within that thing. So all of that thing has high frequency, all of TL, but maybe more. So all you can say is TL is contained in the high frequency set. Okay. Now, you can now forget all of what I said so far. We will now formulate a purely combinatorial problem which comes out of that argument. So here's the combinatorial problem, and you can now pay attention to this afresh, even if you didn't remember all of that. Story of the last while leads to the following problem. You're given a collection of sets S1 through SD. In our setting, SI is a set of documents with high frequency word I. We want to find the minimum number K of sets among these. Those would be sort of catchwords, such that every one of the SI contains one of these sets. So we call this a set inclusion number, SIN. The SIN problem is actually easy. It's a simple greedy algorithm works, okay, which I won't go into, but it does. But our problem is ASIN, actually, approximate set inclusion number. So here's the problem, combinatorial problem. I give you the D set. I want to find the minimum K such that every SI approximately contains one of these K sets. Approximately means it can be missing some S elements where S is specified. So, okay, so let's study this problem a little bit. By the way, I mean, it's a very natural combinatorial problem, but I think I don't know any study of this earlier. So somehow one of these simple set problems that apparently has escaped study, at least to my knowledge. But so one thing I want to remark is, so for the exact problem, you just take the minimum cardinality sets in order. Turns out that's enough. You should never take a set which contains something that's already there. Otherwise, that's enough. Now, for this problem, it's important to require that the sets be among the S1 through SD. If I don't require that, I can just take the empty set, and everybody contains the empty set. So the answer is trivial. So I have to have this. Yeah. So D is the number of words in the dictionary. So each word in the dictionary gives you one S, which is the number of set of documents which have high frequency in that word. Okay, high is defined in a particular way, which I didn't define here. Okay. It's not difficult to show it's NP-hard in general. Okay. The approximate version. The real exact version is, of course, solvable. Sorry? I think the reduction is from vertex cover, if I have up right. Yeah. It's a simple reduction. It's not very so. Okay, so I should say the NP hardness result that we have, that you're also pointed, is a very simple one, but allows a lot of error in the approximate part. It will be nice to prove hardness, various error parameters, we don't know. So again, I don't think this commutative problem has received a lot of study, so maybe it has.
And you want the intersection cardinality to be like a constant, or can it be a constant?
So at the moment, the number of elements it misses from the other set can be order n, small constant times n. So it will be interesting to study other parameter ranges where it only misses a constant number. So in our setting, it's of course not, we solve it a linear time, so it must be positive. So what happens very roughly in one phrase is, in our setting, the drop between high and low is steep enough that very few SI are non-trivial. Okay. So ideally, I would like only k SIs to be non-trivial, only the catchwords, but that cannot be ensured. I don't know the catchwords, so at least at most this many are non-trivial. The rest are just everybody, because I look for a very big drop and I may not find it in general. Okay. So now the last slide, I want to focus a little bit on set inclusion number and sort of a little bit more on how this might apply to other problems. But these are not results, these are more sort of conjectures. So another place where k is assumed given is k-means clustering. So there's very little literature on how to find k in k-means clustering. There is some, but there isn't much. So it's minimized. So the problem is, of course, minimize the k-means objective function, sum of squared distances of data points from the center, right? Under assumptions, there is a well-defined correct k. Now, if I don't, there's no extraneous way of defining k, right? Unless you plot for various k's and take the best or something like that. But there has been a study of a couple of, at least, actually more than this, there are some other places where this has been studied. So if you make assumptions about the data, roughly both these sets of assumptions say the clustering problem gives you, there's a distinct true ground truth clustering that you want to know, and it's well separated from, the clusters are well separated in some sense. I won't go into the details of that. So if you assume these conditions, then there is a correct k, but these literature on this assumes that k is known. It still doesn't find the k, right? So the question is, does ASIN help give a data-determined definition of k like it did for topic modeling? Now, the rough idea, by the way, so maybe I should illustrate this for Gaussians. I didn't draw a slide, but here's a picture. Suppose you have two Gaussians, right? Spherical Gaussians separated by a few standard deviations in d dimensions. So the dimensions of the data point to center is very high, the distance, but they are only a few standard deviations apart. Now I take all possible cluster centers, those cluster centers that are inside the first cluster or very close to the first cluster points, and let's say distinctly farther from the second cluster points, and similarly for the second cluster. But there are points in the middle, and I don't know which points work. There are points in the middle of the two clusters which may be more or less equidistant from both the clusters. So now I put down a matrix which is for each possible center, what are the nearest few points where I make the cutoff arbitrary. So these will be my SI, and you can argue for Gaussians that set inclusion number is the right thing. But the question is, more generally under these conditions, does the set inclusion number give you the right answer? So the sets will be sets of points that are at distance at most r. I think I have it. It's the set of the collection of sets you take is a set of data points at distance at most r to point I. So you do this for every I, and then the conjecture or hope is the set inclusion number gives you the correct answer, right? Okay, that's it. I'm done actually. So we have plenty of time for questions if you have. Sure. Yeah. So you can do binary search, or you can even exhaustively search each case. Only polynomial, yes, right? But then you have to have a way of evaluating how good a K is. That again is arbitrary. So if you are willing to go with these arbitrariness, then yes, then you can. Then there are papers which do that. I mean, there are some arguments that say singular values are the correct thing and so on and so forth, but these are not absolute, right? No. And they are not data determined without looking at, exhaustively looking at all the cases.
So you can't, it's not clear, like you keep doing it for 70 and try to find out how well you check with the data and check with the K value.
You can, but you have to have a criterion which you have to, it's arbitrary in some sense, right? So this wants a principal definition of K from the data, but of course that requires assumptions, unfortunately. Yeah.
How much easier is it when most documents are pure, but the variance is still composite?
Okay, that's a good question. So in fact, in the first paper of Christos and others, the assumption was that most documents are pure. I don't know an advantage right now that you can get if that were true still. There should be, but I don't know an advantage you can get, because you don't know which subsets of documents are pure for each topic, and we seem to have to try all in the existence. Then it's not worth. But the question is a good one. I think one can perhaps get some advantage. Like
I'm asking if this has to do with the question of whether humans and Neanderthals make it, and it's exactly the same problem.
okay, yeah, there you have somewhat some purity. Okay, thank you. Thanks.